people tell? All right. Okay, it sounds like it's on now. Cool. So welcome back, everyone. We're going to do the second part of our two-part series on search now. Looks like we lost some part of our population to the career fair, but still a good number of people here. All right, so this lecture is going to be about two topics. The first one is how to combine machine learning and search. How many of you have heard of the structured perceptron algorithm? All right, at least Daniel over there. Okay, well, TA should be raising their hand. Good, that's new. This is going to be new for people. And the second thing we're going to be covering is A-star search. How many of you have heard of A-star search? Okay, cool. So that might be a little bit of a review, but we're going to go over the properties and guarantees of A-star search a little bit more in detail. So those are the two topics, and let's go ahead and get started. So first, just a quick review of what you learned last time. You saw all of these different approaches for doing search last time. So if you recall from last lecture, we had this problem where we wanted to travel from city 1 to city n, only going forwards. And the cost of going from city I to j was given by this cost c sub ij. So here we have a slight variation of the problem where you have to go from the first city to the last. And once you reach the last, you have to go back to the first city, only going backwards. So if I gave you this new search problem, which of these four search algorithms can apply to that problem? And there's more than one right answer. I'm going to go ahead and reset the counts and give people a chance to chime in and comment on that one. All right, looks like we have trouble with that again. All right, well, in case that doesn't work, just think in your head which of these would work for this problem. Okay, cool. Let's see if this triggered. And we've got a heavier weighting on the bottom two, dynamic programming, uniform cost search, a little bit on the top. The correct answer is the bottom two, dynamic programming and uniform cost search. So why is that? First of all, recall that depth-first search assumes that all your actions cost nothing. So as soon as it finds a solution, regardless of whether it's the minimum cost path or just any path to the solution, it stops. So it doesn't necessarily find you the minimum cost path, and that's why depth-first search doesn't work. Breadth-first search assumes that all of your actions have the same cost. So no matter which city you're going to from which other city, it only works if it has the same cost. And so again, that one doesn't work for this problem either. Okay, so dynamic programming is a little bit trickier. If you recall from last lecture, the main assumption about dynamic programming is that there can't be any cycles in the graph. So you might think, well, this problem should have cycles, right? Because I'm going back to the original city. If you remember from last lecture, the dynamic programming graph for the original problem looked something like this. From 1, you can go to 2, to 3, to 4. From 2, you can go to 3 or 4. And from 3, you can go to 4. And if you're going backwards, you might think, well, maybe there's an edge like this going back in these directions. And that would cause you to think that there's a cycle in here, and therefore you can't use dynamic programming. But this is actually the wrong graph. Because suppose you have an edge here that goes to 3. On your way back, you can't actually visit cities that are later. So this node isn't an accurate description of where you are on your way back. Really, the better way to think about it is that really you've constructed a whole new set of nodes going this way. Didn't really draw this in the right amount of space. Over here, so you essentially build a set of mirror nodes of the cities mirrored backwards, and you run search in that direction. And so then if you look at this whole graph combined, it's actually still acyclic, and that's why you can use dynamic programming there. Uniform cost search would have worked even if there were cycles, and the costs just need to be positive. So all the costs are positive in this problem, and so you can use uniform cost search. Okay, so we're going to do a quick review. Last time we talked about this notion of state, which is a summary of all the past actions you've taken, throwing away everything you don't need, such that you can choose future actions optimally. So in this case of cities that we're visiting, all the previous cities that we visited don't matter in figuring out how to get to the end optimally. All right, cool. And this notation we're going to use again for this lecture. So sstart is the starting state where you start in the search problem. Actions of S returns the possible actions that you can take in any given state. the cost of a state and an action. So it's saying what's the cost of taking this action in this state S. And the successor function, which you can really just think of as next in your head. So if you're at state S and you take action A, what's the next state that you arrive at? And finally, is end, which is just asking us, for this state, have we reached the end, right? Okay, and as always, throughout all of this, the objective has been to find the minimum cost path going from some start state to some state that is the end. Cool, so that's all review. Last time I promised you that we would look at learning in the context of search this time. We talked about modeling and inference. So recall that modeling is the task of setting up that graph and deciding what the actions are, and inference is actually finding a search route through it. So what's the learning problem? It seems like we've specified everything. The learning problem in this case is going to be a situation where we don't actually know the costs of taking actions, and we need to somehow learn those costs. We'll get into a little bit more detail with that. But let's dive into the first part, and then we'll get to A-star search next. So suppose we're doing this transportation problem that we've been looking at last time. So the problem is you're in some city, and you've got to walk n blocks. You don't have to walk. You have to get to the last block from the first one. And at every block, you can either walk to the next one, which costs you 1, or you can take this magic tram that doubles the block that you're at. So, all right. We had some search algorithms that we looked at last time, and they produced solutions that look like this. Walk, walk, take the tram 3 times, walk, and then take the tram again, right? Cool. So learning is this problem. Learning says, suppose that somebody showed me what they actually did, but I don't know their preferences for whether they like to walk or whether they like to take the tram. So I don't know what cost they associate. Maybe they really hate taking the tram, and the tram cost is 100, and walking is like almost effortless for them, so it's 0. So how do you figure out, if they give you a demonstration of what they do, what are their preferences? So the learning algorithm will try to back out or reverse engineer their internal cost function. And you can kind of imagine that being useful in, say, some sort of app. Let's say it's, in the most basic case, giving navigation directions. One person might prefer to take routes with less traffic. One person might prefer to take routes with more trees. We're trying to infer what their preferences are. So the forward problem that we did last lecture goes from a set of costs to some optimal path. And the learning problem today is backwards. So somebody gives us a sequence of actions that they think is optimal for them, and we have to figure out what their cost function is. Okay, so let's make that concrete with this problem. So this is the same walk versus tram problem that we've been looking at. You have to get from city 1 to city 4. And this is the search tree that you have. It's actually missing one edge, which allows you to take the tram from 1 to 2. But otherwise, it's the entire search tree. And let's say that somebody said, for me, the optimal path is to walk 3 times. So, all right, let's say that we think walking costs 3 and taking the tram costs 2. So if that were the case, then it would actually be better to walk once and take the tram, because the total cost is 5. If you walk 3 times, the total cost is 9. So our belief about what their costs are is inconsistent with what they did, right? But on the other hand, if we adjust our costs, intuitively you think, well, walking is too expensive to explain what they did, so let's make walking cheaper. So you subtract 2 off of walking, and now the path that they took is actually better than the alternatives. And that's the main idea. We're going to try and adjust the costs until it matches what they did. Any questions about the basic setup? Yeah? Oh yeah, so that's just a mistake in the notes. There should also be a tram option from 1 to 2. Yeah. Other questions? Okay, cool. So let's get into the structured perceptron, which will be giving us a way to figure out these costs. All right, so to start with, we're going to make this assumption that the cost function is actually not going to depend on the state. So we're going to assume that for any action, no matter where you take it, it's going to have one cost. And the way we're going to write that is we're going to have this variable w. You can think of w right now as just like a Python dictionary, which takes in an action and returns a cost. So notice that it doesn't depend on the state. Just think of it as a dictionary. Okay, so if somebody outputs an actual path, I can look at the actions they take, and I can look up the cost in my dictionary, W, for each of the steps, and then I add the costs together, and that's the total cost of the path. You just add them together as we've always been doing. Okay, and now with just that little bit, we can actually introduce the most basic version of the structured perceptron. So what we'll do is we'll start by pretending all the costs are 0. That's just our way to initialize the costs. Every action costs 0. And then what we'll do is we will iterate through a set of training examples. So what are these training examples? So D sub train is a big collection of XY pairs. And this is probably familiar to you from the earlier classes of kind of learning algorithms have these XY pairs, input-output pairs. But what are they actually in this setting? So in this setting, X is an entire search problem. So X is actually some tree, some search tree that we give to you. And maybe there are many different search trees. And for each search tree, Y is going to be some optimal path through that tree. All right, so far in the previous lecture, there was only one problem and one solution. Now we have many search trees with many solutions. Each one is an X comma Y pair. So what we do then is, given that search problem, we use our cost function that we think is correct, this W at the top, and compute a path that is optimal with respect to what we think the costs are. And that gives us Y prime, which is not the real solution, but our solution under our costs. And then what we do is we look at the true solution, so that's Y. Y is the solution given to us by some user who's trying to tell us their preferences. And for every action along their optimal path, we reduce the cost of that action. So if the user, let's say, walked 3 times, we reduce the cost of walking by 3. And if they took the tram twice, we reduce the cost of taking the tram by 2. So all the costs seem to be going down, but we have a counteracting force. So Y prime is the path that we thought would be correct under our estimate of the costs. And for all of the costs along that path, all of the actions along that path, we increase the cost. So that counterbalances the first update. So you can kind of get an intuition for this, that we're roughly trying to reduce costs along the true path that we saw and increasing costs anywhere else that's sort of competing with the true path. Any questions about this pseudocode? All right. So let's just do that in code now. Whoops. OK, so the first thing we're going to do is, I've already got the code here, but I'm just going to build it out for you. So the first thing we want to do is generate a bunch of examples. These are the XY pairs that we saw in the pseudocode. So this example generation function is going to be our simulation of a real user who has some preferences. So it actually knows the cost of walking. Let's say the cost is 1, and the cost of taking the tram is 20. This we don't show to the learning algorithm. This is what the learning algorithm has to guess. Then what we'll do, and let me go ahead and print that out, is we'll generate a bunch of examples. So in our case, we want to generate, if you recall from last time, we had this transportation problem that was about taking walks versus the tram. And we're going to generate actually not one transportation problem, but let's say 50 different transportation problems. So we'll do for n in range 1 through 50. OK, that's not quite 50, but that will do. So for each one of these, we'll say, OK, so the input to the problem will really be defined by just one number n, which is the ending block that I need to end up at. And then we want to have some optimal path for that problem. So predict is a function I haven't defined yet, but it takes the problem definition, which is just n, and it produces an optimal path for that problem. So it's going to be some sequence of taking the walk and taking the tram. All right, and it looks like there's a question back there. So let me just make sure we got this down right. OK, question in the back.
Can you just increase the font size?
Oh, yeah. OK, I keep forgetting to do that. All right. How's that? OK, cool. So this will give us a set of examples. And now I haven't actually defined predict, which is the function that actually produces the optimal path. So let's do that very quickly. Okay, so predict takes a problem definition, which is just given by a number. It takes the user's preferences for how much it costs to take a various action. And what it does is it actually instantiates a transportation problem like we saw last class. And that just took a number n. But now we're going to add one more thing, which is the cost. So the problem needs to know about the costs. And then we'll call some search algorithm that we used last time. It really doesn't matter which, as long as it returns the optimal path to solve the problem with respect to the real preferences. And then I've just got one last line here, which extracts out the optimal actions from the optimal history produced by the history variable right here. So that's the predict function. Okay. Now we're actually in a position to actually define the structured perceptron algorithm. Okay, so it's going to take the set of examples that we generated earlier. And as I said in the pseudocode, we'll initialize the weights to just be 0. And now we start to make learning iterations. So we'll cap it at a maximum of 100 iterations, although this will probably converge faster than that. Oh, and I should say something about the convergence guarantees with the algorithm. So the one that we just saw, if you have a set of weights that actually manages, if there is a set of weights that actually manages to get completely 0 error on all of the training examples, then this algorithm will eventually converge to a set of weights that achieves 0 error. That's something we're not going to prove here, but it's something you would want to know if you actually ran this. All right, so let's now iterate through the examples. Oops. Cool. So the first thing we'll do is make a prediction of what would be optimal if our weights were correct. So those are the predicted actions. And then for each action in the true set of actions, we're going to take the cost for that action and downweight it by 1. And then for each action in our predicted actions, we'll upweight the cost. Okay, so as written right now, this thing doesn't terminate at any point. But once we eventually hit 0 error, in other words, once we're able to accurately predict all of the paths, we want to stop. So let me just add a little variable here to keep track of how many mistakes we've made. And we'll check if we have a mistake by seeing if our predicted actions match the true actions. If they don't, we'll up the mistake counter by 1. And after we've looped through all the examples, if we made no mistakes at all, then we can terminate the algorithm. And let me just add this one line here to print out how well the algorithm is doing after each iteration. So that's the whole structured perceptron algorithm. I got a question over there.
Just one comment. I don't think you can do the bang equal in Python. You do not equals.
The bang equals. No, you can do bang equals in Python. Yeah. Cool. Let's see. Any other questions? All right. So let's go ahead and run that now. So we've got a set of examples that we'll generate. And then we will not print the training data set for now. Let's just, actually, let's print the training data just so you can see what it looks like. OK. OK, that's too many problems. Let's make it smaller. OK, actually, maybe we can look at this. So here's the set of problems, iterating from the problem where we just have to walk 1 block all the way up to 22 blocks. And then after that, my line wrap starts getting messed up. But these are all solutions to the problems according to these different problem specifications. Actually, they look a bit suspect because they're all walk.
Because we made a tram 100, right?
Oh, yes, that's right.
20
I actually made tram 20. OK, yeah, so maybe that's why. Cool. So now let's go ahead and run the structured perceptron algorithm on this and see what we get. OK, so recall that in here, generate examples, I made tram taking very expensive. All right, so let's interpret each line here. This is the iteration that we're on in the algorithm. This is the number of mistakes that we're making. You can see that as it iterates, it eventually goes down and hits 0, right? And the weights are gradually being updated until we converge to a set of weights that are 80 and 4. So 80 and 4 is not 20 and 1, right? But the number of mistakes is 0. So why is it? Why is it that we're able to get 0 mistakes even though the costs are off? And I know you know the answer. To see if anybody else wants to. Okay, over there.
Well, because like the costs are just scaled from.
Yeah. Okay, so the answer is that the costs are relatively scaled correctly. And under any scaling, doesn't matter what, as long as it's not a negative scaling, the behavior of the person is going to be the same. So actually, the set of examples we saw do not uniquely identify a set of costs. And you probably heard this term elsewhere, but that means the problem is unidentifiable. That's when your data does not uniquely identify a set of parameters. Nonetheless, once we hit number of mistakes equals 0, we terminate. And why is that? So if you look at this algorithm here, these two lines, if you focus on that, so if true actions and pred actions are the same, right, then we increment by the same amount we decrement, and basically we don't make any updates anymore. So we can just terminate there. All right, and that's basically the most simple version of the structured perceptron. There's a generalization of this to the case where you don't assume a fixed cost for every action. So the same action in different places, we can assume that they have different costs. And in fact, you can even extend this architecture to handle cases where you have an infinite number of actions, as long as you can describe each action using a feature vector, the same sort of feature vector that you were thinking about in the earlier reflex-based models. I won't go over this right now. If we have time at the end, we can talk about that generalization. But now let's go on to talking about A star. But before I finish, actually, let's first talk about some applications of this perceptron algorithm. So I already said that you could use this to infer a user's preferences if they're showing you paths that they navigate. But there are really far more applications than that. So here's an example where we want to actually take a sequence of words and produce a set of part-of-speech tags for those words. Here's another example where we're translating one sentence into another. So what does this have to do with structured perceptron? Well, generating a sequence of words is essentially doing a search problem where you're choosing words to pick at every time step. And the words that you pick are influenced by the input. So if a translator shows you a bunch of translations they give you, internally you can think of it as they're doing a search problem where they're following some kind of cost function that prefers to translate certain words into certain other words and prefers to line up words such that they're grammatical. And what we're doing is attempting to learn that cost function that prefers valid grammatical translations. And we can talk later about exactly how that's implemented, but something like structured perceptron is a basic approach to going about building such a system. All right, so now we're on to the next part, A star search. Oh yeah, question.
Just before we move on, how robust is this if you have like a little bit of error in your training set, like if maybe a couple of your paths are not 100% optimal?
Right, so the generalization of this algorithm is actually, you can show that this, the question first of all is how robust is this if you actually have a set of data that is maybe not self-consistent. So the demonstrator is not being optimal with respect to their own cost function. So you can actually show that this algorithm is performing gradient descent on a particular objective function, which we can talk about later, and it will still converge. But whether it converges to what is the true cost, that depends on what kind of noise is added on top of the paths that you see. Cool. Any other questions about that section? All the way in the back there.
Yeah. Will it always converge to multiples of the cost function, or it can converge to something different?
So the question is, will it always converge to a multiple of the cost function? So the actual theory says that if there are solutions that get 0 error on the training set, this will converge to one of them. And so in this case, multiples, I think, are the only solutions that apply here, and so it'll converge to some multiple.
What if the costs also depend on the state?
Right. So that's the generalization that I didn't show here, and maybe we can get around to that if I still have time at the end. The question is, what if the costs depend on the state too? And there is a way to handle that as well. Cool. All right, so now we're going to talk about A star search. The big idea with A star search is the following. Actually, before giving the big idea, let's just compare, let's see A star in action and see how it works. So you remember that uniform cost search kind of emanates uniformly out from the start state. A star search ends up looking more like this. So there's a very small green dot in the upper right corner, which is where the search algorithm is trying to get to. And it's starting in the bottom corner. And you can see that it's somehow prioritizing directions that seem to be getting closer to the real end state. And we'll see how it manages to do that in the next few slides. This seems a lot more efficient than just emanating out uniformly from every direction, right? Okay. So how does that work? The basic intuition is as follows. So uniform cost search, as we saw, emanates out in every direction uniformly. And consequently, you would think that all of the time spent going in the wrong direction is wasted effort, right? Somehow we'd like to be able to tell the algorithm that it should not be moving farther away from the end state. So we want to somehow incorporate knowledge of how far we are away from the end. Okay, so recall that uniform cost search prioritizes what it searches in order of the cost it takes to reach that state. I want to actually give a quick demonstration of uniform cost search again, because some people asked me about this last time. So let's just quickly review uniform cost search again. Suppose that you start at this start state and want to get to this end state here. And people said, well, what happens if one of the paths looks cheaper in the beginning, the other one looks more expensive in the beginning, but in the end, the more expensive one turns out to be cheaper, and the seemingly cheap one turns out to be expensive. So how does uniform cost search actually handle this? Recall that we have some initial state that we've explored, and the frontier is everything we can see from this point, right? So in the frontier, we're going to say A1 can be reached with the cost of 1, and B1 can be reached with the cost of 3. Now, uniform cost search looks at what's in the frontier and picks the cheaper one. So it goes to A1 right here. And now what we can see on the frontier is A2 and B1. So we'll take A1 out. And I want to emphasize again that once something has been put in the explored set, it can never go back into the frontier ever again. All right, so now we have A2. And what do we put as the priority for A2? We do not put 1. We put 2, because that's the entire cost required to reach A2. That's the thing I want to emphasize, that this priority queue is scoring based on the entire cost necessary to reach a state. And so what you'll see in this problem is that initially this path will race ahead and get to A2, but when it sees this 6, it will kind of balk and say, getting to T this way is really expensive, and the priority of going this way will be smaller and will actually finish first. So I just wanted to give that example really quickly. For A star, we're going to, instead of using the past cost, imagine that we had access to the future cost as well. So now the entire cost of a path is just all the cost before S and all the cost after S. So we don't actually have the future cost function, because if we did, we'd have basically solved the problem already. But the idea of A star is to get some estimate of the future cost, which is this heuristic function H. And essentially, the entire A star algorithm is this line right here. So it's just like uniform cost search, except instead of exploring by the past cost, we add this extra H of S, which gives us an estimate of how much cost is left. And the intuition there is that if you're going in the wrong direction, H of S will be very large. It will say, hey, we're going farther and farther away. Your remaining cost is really high. Question here.
Is there a reason why we're calling dexterous uniform costs when the costs are not uniform? Is there something I'm missing?
Oh, yeah. So we're calling dexterous uniform cost search because at any given point, we're sort of uniformly expanding the frontier in the sense that things on the frontier all have roughly the same cost. So it's not that all the costs are the same. It's that the cost to reach a node, the frontier, it consists of nodes for which the cost is roughly the same. Yeah. Question?
So the heuristic function is constant in Dijkstra's?
So the question is the heuristic function constant in Dijkstra's? Right, so in Dijkstra's, you can basically think of the heuristic function as being a constant because then it doesn't affect anything, essentially. All the priorities stay exactly the same if you just add a constant to something. That's one way of thinking about it, but really it's better to just think that h of s is 0 in Dijkstra's. There is no estimate of the future cost. Okay, so that is literally the most important description of A star right there. And what might this heuristic cost function actually look like? So one way you can imagine this is, let's say your search problem is that you're navigating through a city, you're driving a car, and you're trying to get to some destination. So you can't easily compute the future cost because that involves imagining going through various streets. But what you can easily compute is, suppose you could just kind of pick up your car and fly directly to the destination. And you could say, well, how long would it take to just fly straight there? And that would be a straight line, so it'd be easy to compute that path. The heuristic function might just be, well, what would the cost be if I just flew directly there? So it's an approximation of the future cost, but it's something that's super easy to compute. That's what the heuristic function should be. All right. So now I want to show you a different formulation of the A star search algorithm. I already told you the simplest formulation, which is that we prioritize now by past cost plus h of s. Now I want to also describe this in a different way. So the way we're going to describe it now, actually, is that A star search is simply just uniform cost search with a different set of costs. So here's the diagram. Let's say we're going from A to B to another state, and finally to some end state here. All right, and we've got some costs C1, C2, C3, C4. Okay, so uniform cost search, let's say we're looking at this path right here. Everything from the start state to D. So what is the cost of, what does uniform search consider the sort of cost of this path? Can somebody just shout it out? Or maybe I'll take a raised hand. All right, right here.
C1 plus.
Okay, yeah, the answer is just C1 plus C2 plus C3. That's how uniform cost search perceives the cost of this path. Now, we said that A star perceives the cost like this. So it's C1 plus C2 plus C3. We still have the same past costs, but now we add one more term, which is the heuristic function's value at D. So this is saying how much cost does it think is left to go. That is the prioritization function for A star. And now what I want to do is write A star in another way such that it reduces to something that we can plug into uniform cost search. So I'm going to say that now I'll modify the cost to be C1 prime, C2 prime, and C3 prime. And the uniform, we're going to say that the cost for this path is the sum of these C1 prime, C2 prime, C3 prime. So what am I going to define C1 prime as? I'll define it as C1, the original C1, minus h of A plus h of B. Okay. Then the second term is going to be, just show that here, C2 minus h of B plus h of C. And the final term here is going to be C3 minus h of C plus h of D. Okay, so if I add these three terms together, what do I get? Well, first of all, notice that the h of B here cancels with the h of B here, and the h of C here cancels with the h of C here. And more generally, if I have more terms, all of the intermediate ones cancel, so that all I'm left with is C1 plus C2 plus C3 minus h of A, the start one, and plus h of D, the last one. Okay, so you'll notice now that this formula is almost the same as this one, right? With one difference. There's this extra minus h of A here. But remember that all of the paths that we explore in the entire search problem all start at A. So they all have this minus h of A here. So this h of A is just a constant that we can ignore. Otherwise, this is now the same as this. So it has the form of uniform cost search in the sense that we're just adding together costs, but it has the value equal to this prioritization scheme. So the key point I'm trying to make here is that if you want to implement A star, you can just change the costs on the graph to these C1, C2 primes, and then run uniform cost search. So we've reduced A star to uniform cost search. And this will be useful in proving a few other things about A star. I want to make sure that this point goes through. So any questions about this right here? OK, cool. So this seemed like just kind of a weird algebraic hack to put A star into UCS. But another way that you can think about this intuitively is that if you're adding the h at the next step and subtracting the h at the current step, what h is really doing is adding a penalty to each cost for going farther away. In particular, if h of s looks like this, 43210, where h is estimating how far you are away from the end state, once you perform this modified cost, you'll see that the cost of going towards the goal become lower and the cost of going away become higher. OK, so will any heuristic work? If we just come up with any heuristic, will we get a more efficient, better search algorithm? And the answer is no. So suppose that we have some h of s that is completely lying to us about how much cost is left to go. Here, it says, after you've taken this step right here, it says, oh man, there's so much more cost, like just don't even bother. And then on the top, it's saying, oh, everything's free, just like go ahead. That will cause the search algorithm to actually explore the top thing first before the bottom. And if you remember, for uniform cost search, once it finds a solution, it terminates, because it assumes that it's not going to find anything cheaper later on. So the heuristic lying to us is very bad. And another way you can see why this is problematic is if you take the heuristic and you modify the costs according to what we just did over here, the costs become these purple values. And what you'll notice is that one of the costs is negative. And we said last time that if you put a negative cost in uniform cost search, it doesn't work. So that's a second way of seeing why this won't work. OK, so then what do we actually need to guarantee that A star will work? What kind of heuristic is definitely going to be OK for us? And the answer is this consistency condition up here. So it looks like a lot. Let me write it out in a slightly different way to maybe clarify what the consistency condition is saying. So recall that successor s comma a is the state that you get to after you take action A. So I'll just refer to that as s prime as the next state. OK, so you can also write this as the cost of s comma a is greater than or equal to the cost of h of s minus h of s prime. So what is this term on the right here? This is kind of saying, all right, I was at s before, and this is how much I thought was left to go. And now I'm at s prime, and this is how much I thought was left. So you can think of this difference as the amount that the heuristic thinks it takes to just cross this one edge, right? And this is smaller than the actual cost it takes to go from s to s prime. So in some sense, you can think of the consistency condition as saying the heuristic is always underestimating the cost. It's always overly optimistic. If it's overly optimistic, then it's consistent. And there's a second condition for consistency, which just says that when you reach the end, you should report 0, because there should be no more cost to go if you're at the end. But the more important condition is this top one, which is sort of an overly optimistic condition. All right, so why is this overly optimistic condition good enough to give us a working A star search algorithm? We want to show that basically, if we use this heuristic, we will get the minimum cost path back. And here's the argument. So consider any path that you take in the graph. Doesn't have to be the optimal path, just any path. So we're operating with these modified costs, and we're running uniform cost search. So the purple up there is the modified cost. And we can expand that out to be in terms of the original costs, which are in blue, plus the heuristic minus the heuristic, using the modification that I just described. So here's the big idea. If you add up the modified costs, the total cost of the path, then you get this big term right here. And that in turn equals the original costs plus the heuristic for the final state minus the heuristic for the initial state. So what happened to all the intermediate terms? They all canceled out according to what we showed right here. So they all canceled out. So what this tells us is that when we're running uniform cost search with the modified costs, the cost of a path is just the original cost plus these terms. But the thing about these terms is that h of s sub l is the heuristic at the final state. So that's 0. And now h of s sub 0 is the heuristic at the starting state. And all the paths have the same starting state. So this is just a constant. So what that tells us is that the cost of a path in A star search is the same as the cost of a path in the original UCS algorithm. So if that's the case, if UCS finds the minimum cost path, then A star will find the minimum cost path too. That's the key idea. I think this is algebraic. It doesn't really give you any intuition about why it works, and so don't expect to have one. Unless you have one, then let me know. Okay, so that's the proof of why A star gets the minimum cost solution. Now let's talk about efficiency. I think efficiency is a little bit more interesting. So efficiency in terms of these search algorithms is all about how many states you explore before you find a solution and terminate. So in UCS, because we're exploring according to the cost it takes to reach a state, that's the past cost, we will explore every state that costs less than the end state, right? So that's this inequality right here. Any state S that's less than the cost of the end state, we'll explore it. And it turns out that for A star search, we'll explore every state S that's less than the thing on the right now. So it subtracts out h of s. And why is this true? So let's write this up and have a look. All right, because we know that A star search is exploring in order of past cost s plus h of s, right? Then we know that it will explore everything s sub end plus h of s sub end. So it's probably easier to see why this is true, that we'll explore every state for which this value is less than this value, right? But h of s sub end is 0, because that's what a consistent heuristic requires. And then we just move this h of s over to the other side. And that's what gives us this condition up here. So, oh, and the proof is just what I just did on the board. So the interpretation is that you want to explore as few states as possible, right? So you want the right-hand side to be as small as possible to limit how many states you explore. And to make the left-hand side, the right-hand side small, you want h of s to be as big as possible. So the bigger the h, the better. And what does a big H mean? It means that h is pessimistic. It means that it thinks that there's a lot of cost left to go. That's what a good heuristic is. But at the same time, okay, well, I'll get to that in a second. So here's a visual description of what that looks like. So uniform cost search explores in a ball uniformly. If you were to choose the perfect h that predicted the exact future cost to go, it would actually go in a straight line from the start state to the optimal end state. And maybe we'll give an example of why that's the case later. But if you have an imperfect heuristic, then uniform cost search will kind of explore in this sort of, you can imagine it as an ellipsoid where it's sort of biased towards the right direction, but might still take a few steps in the wrong direction. Cool. Any questions so far about that? Okay. So the key idea here is that A star is distorting the cost of the edges such that edges that move away from the end state cost more. That's the main thing that you really want to take away from this. And I'm going to bring up this idea of admissibility because usually when you hear about A star in maybe in other contexts, they'll say that admissibility is the condition required to actually make A star work. So what is admissibility? Admissibility just says that H of S underestimates the future cost. So we can prove fairly easily that anything which is consistent is admissible. I'm not going to do it right here, but the intuition is that with consistency, we saw a condition that sort of says that H of S underestimates the cost of every individual edge. So if it underestimates the cost of every individual edge, it must underestimate the sum of those edges going all the way to the end. That's the rough intuition for why consistency will imply this admissibility condition. So admissibility is a sort of stronger requirement. Okay, because we went through a lot of proofs and inequalities just there, there's a whole section just for relaxing where we don't do anything at all. But just kidding. This section is actually for giving you a recipe for computing and defining good heuristics. And it's going to be through relaxation. So here's the main intuition with this. Ideally, your H of S would be a perfect estimate of all the future costs that's left to go. But that turns out to be just as hard as solving the original problem. If you knew that future cost, probably the only way you could get it would be by doing the search problem. So the main idea here is to formulate a new problem where we don't have all the constraints of the original problem and compute future cost in that relaxed problem. When you remove constraints, we'll see that you can actually make things easier in 3 ways. So one is if you remove certain constraints, like, so for example, the example I gave of a heuristic earlier where you can just pick up your car and fly to the destination, the constraint you're removing there is all the buildings, all the streets, all the people that you might run over in the process of doing that. And once you remove the constraints, you can get a closed form solution, an easier search problem, or a problem where actually the problem breaks up into independent subproblems. And we'll also see a technique for combining multiple heuristics, if you can come up with multiple heuristics. All right, so here's a concrete example. Let's say you're trying to get from this triangle to this circle. To estimate the future costs, the only reliable way is to actually do the search problem to get there. But if you remove the black squares, then now estimating future costs in this relaxed problem is easy, because you just subtract the x-coordinate difference and the y-coordinate difference, and you have an estimate of how to get there. So that's an example of a closed form solution to computing future cost in a relaxed problem. We can also look at this tram problem that we were looking at earlier. So this is the same problem that we had before, but suppose now that you have one extra constraint, which is you can't have more tram actions than walk actions. So we saw this sort of problem in a quiz earlier. You have to actually augment your state with a little bit of extra information to make sure you balance out the tram and walk actions. And the solution that we proposed at that time was to take our current location, but also remember the difference between the number of walking actions and the number of tram actions. This difference is necessary to make sure you don't do too many of one action. But now, that blows up the state space of our search problem. So we went from having O of n states, which is just the number of locations, to O of n squared states. And that means that you're going to have to do more computation. So that's expensive. What you can do with A star search then is say, I'll define a heuristic function which says, let me just pretend that that constraint didn't exist. So I'll just remove the constraint. And then I'll say, okay, well, if this constraint didn't exist, what would the future cost be? And in that problem, we only have the original location as the state now, right? And we know how to solve this problem because we wrote a dynamic program to solve it last time. So we can actually use this dynamic program to compute the remaining future cost in the relaxed problem. And that becomes our value for H of S. So what might be unintuitive here is that we have the original search problem, which has these new constraints, and it's calling this function h of s. And for every call to h of s it makes, that function actually sets up a small mini problem and solves it using dynamic programming. So we're doing a search, and inside the search, we're doing a smaller search on a simplified problem. That's the idea of doing easier search for your heuristic function. All right, let me just write out those steps. So we're going to define this relaxed future cost function. So it's future cost sub relaxed. And that is the correct optimal future cost in the relaxed problem where we don't have to balance our tram and walk actions. And then we're going to basically say that h of s in the big problem, the main problem, is equal to this future cost in the other problem. Any questions about that? I feel like there should be some questions about this, so I'm going to wait longer. Okay.
In the context of this particular problem, where it's a pretty simple operation to keep track of the difference between the number of walks and number of trams.
Yeah, yeah.
Is going for this relaxed sort of problem as our heuristic more complex than just the original idea?
Yeah, so the question is it really worth the trouble to run this heuristic where you're actually running a DP inside the heuristic? So the main point that I want to make is that the original problem is only O of n, and the new problem is O of n squared. So O of n squared, if n is big, that can be way bigger. And if you run the heuristic, which is quite cheap, it's quite possible that you only explore a much smaller set of states than the O of n squared. It really does depend, though, on kind of the shape of the search tree, so it's hard to say whether it's worth it or not. Other questions? Over here.
In the worst case, would it not help at all? Is there any way the heuristic could help, could hurt the complexity, the time complexity?
The heuristic could hurt the time complexity, yes, because you're spending, so the question is, yeah, in the worst case, can the heuristic actually make your algorithm run slower? And an example of where it would run slower is, let's say that your heuristic, you define a relaxed problem which is identical to the original problem, and you're running that as your heuristic. So then every step of search, you're doing the whole problem over again. So that's got to be worse than just doing the problem from scratch.
Wouldn't that just be a bad heuristic?
That would just be a bad heuristic, yeah. Okay, other questions? All right, we're going to be phenomenally under time again, which is why I'm stalling. So, okay. Okay, another question. Yeah.
Why would you have to run the problem again every time? Couldn't you just solve the simplified search, like hash the results? And
Oh yeah, that is a good point. Sorry. So yes, I said that to kind of draw attention to the fact that we're solving like a subproblem inside. But the point was that you actually only need to solve the relaxed problem once. You just need to run the DP to compute the optimal future cost for every individual state, and then you just remember it, and then you just look it up for future states. So that's a really good point. Yeah. Other questions or comments? Over here.
If you suspect, for instance, that you're not going to explore most of the paths, could you compute the heuristic at each point instead of doing like a DP solve the entire relaxed problem ahead of time if you think you're not going to need most of it?
Yeah, that's a cool idea. So the proposal is that if you know that you're not going to query the heuristic at a lot of states, then maybe you can opportunistically only compute the solution at some of the states. So for the dynamic program in this problem, you have to like look over all the states, but there are, the heuristic does not have to be solved with dynamic programming. It can be solved with any search algorithm. So if you have some search algorithm that only explores out to some depth that it thinks is interesting, then you can also save a bunch of computation that way. It's a good point, yeah. All right.
Could you use a heuristic to solve a heuristic?
So like, yeah, yes, that's true. So okay, the proposal is that you could have a heuristic function that itself has another heuristic in it. But with two heuristics, we're going to see a way of combining them. I don't know if it strictly dominates what you're saying. Maybe it does actually, but that's also a really cool idea. All right, cool. So now let's go on to one more example of a heuristic. So every one of you has probably seen one of these puzzle problems where you have to move the tiles around until they're all ordered correctly. And the tiles cannot, you kind of have to get one tile out of the way to move another tile. So in this problem, the constraint is that you can't move a tile in any position in any direction. And one idea you can have is to relax that constraint and say, what if the tiles could overlap? So if the tiles could overlap, suddenly you can actually solve 9 or 8 independent problems. For each tile, you just move it directly to its location. And in fact, there's a closed form solution for doing that because it's just the difference in the x-coordinate and the difference in the y-coordinate. So that can be your heuristic function. How many steps does it take to get to the solution if I just move everything independently? And that's an example of what we call independent subproblems. Okay, so I've given you several different examples of how to remove constraints, but I haven't given you yet a general principle for coming up with these heuristics. And in general, being able to come up with these is quite useful. Like if you're playing a game like StarCraft or something and you want an agent that can operate on that, one thing you might imagine doing is, well, I'll do all of these sort of, attacking other players as an independent problem, building up resources as an independent problem. It's sort of a generally useful strategy. But we still haven't given you any theorem about how to guarantee that your heuristic works. And the general idea is that in the relaxed subproblem, the costs always have to be smaller than the original problem. That's the main idea. And in fact, you can think of a constraint as really just an action that is infinitely expensive. So for example, here in this problem we saw earlier, walking into a black square, instead of saying that's not possible, we could just say that it's infinitely costly. So a relaxed search problem is a problem for which every single cost is less. And a heuristic function is basically just, in the relaxed problem, the true optimal future cost. So the relaxed problem should be so easy that you can actually figure out the true future cost. And your heuristic is just that future cost in the relaxed problem. And that's the general framework. So why does this framework actually work out? It works out because if you lower bound all of the costs, then you end up with a consistent heuristic. And let's give a quick proof of that. So the first step is the following. I want to show you why this inequality is true. All right, so suppose you're starting out at some state S, and you've got a set of costs that you can take. So we're in the relaxed problem right now, so I'm going to call the relaxed costs R1, R2, and R3. These are the costs for taking these actions in the relaxed problem. And then there's some future cost for each one of these, future, etc. And we'll call these S prime. So recall that then this future cost here is really h of S prime for each one of these. So what we know is that h of S, the future cost at this node, is equal to, let's say this is the optimal path right here. Then h of S is equal to R2 plus the future cost, right? Which means that h of S plus R2 is less than or equal to any of the other options. So h of S plus R1 or R3, right? So in this formula over here, this is the R that I have on the whiteboard. And we're saying h of S is less than R plus h of the future state, h of S prime. So it's always the case that h of S is less than this quantity over here. And then we know that this relaxed cost is always smaller than the real cost, because that's the condition, that's how our framework works. All the costs have to be smaller. And if you were looking closely at the condition for consistency, this right here is the condition for consistency. So that gives us the proof that if you lower bound the cost, you get a consistent heuristic. Okay, so at this point, you've probably heard me say that a consistent heuristic is one that's overly optimistic, right? But I also said that an efficient heuristic is one that's as pessimistic as possible. So those seem to contradict each other. And indeed, they're sort of competing forces. So when you relax a problem, you're inherently making it more optimistic because you're removing constraints. And removing constraints is exactly what makes it easy to compute a heuristic. So the game that you're trying to play is you're trying to relax as few constraints as possible to make the computation cheap. But you don't want to relax too many because you don't want your heuristic to be too optimistic. The more pessimistic you can make it, the more efficient it'll be. So that's the tension between those two things. And that's kind of what this slide is about right here. The last thing I'm going to cover, and the proof here is going to be exercise left to you guys, is what if you have two heuristics? An easy way to combine them is to actually take the max of those two heuristics. And this is nice. You like the max because the more pessimistic the heuristic is, the better. And taking the max always makes it more pessimistic. And there's a proof that the max is also consistent. So this is a tool that you can use whenever you want. You can throw as many heuristics in there as you like, as long as they're all cheap to compute individually. Cool. So we've pretty much gotten to the end of the material. Let me give you a quick summary. So today we talked about the structured perceptron, which combines search and machine learning to give you an approach for learning costs. A quick aside about this. So the structured perceptron combines a search algorithm, something like Dijkstra's, and the perceptron, which is a learning algorithm that you guys probably saw earlier. Those two algorithms were both developed in the 50s, 1 year apart from each other. But the structured perceptron actually came 40 years later in the 90s. So this is possibly one of the most recent things that you've learned in this course. We'll get to more recent things in future lectures. Okay, we talked about A star, which gives you a way of adding heuristics into search. We talked about relaxation, which is basically a recipe for allowing you to come up with heuristics. And next time, Percy will be coming back, and we'll be looking at doing search problems in an environment where there's noise. So what happens when you get on the tram, but it doesn't reliably take you to 2 blocks later, but gives you some random location that you end up with? How do you search in a context where there's noise? And that is all. Thanks.